Okay, Assalamualaikum and a very good morning. So today we reconvene our lectures. So my apologies for the Monday lecture. So I just had too many things to do. So let me share the screen first. Okay, you should be able to see my screen. Please confirm that. Okay, so today what I'm going to do, I don't have typewritten notes as just like before. I'll probably have to do this on the whiteboard and probably type this later on. I already finished the previous lectures on typewritten, but have not gone for today's one. So today we are going to see essentially some applications of how we define entropy, okay, with respect to some states in certain examples. So I'm just following the book up. Oh yeah, but I will have to give you the assignment around this afternoon. Okay, so the assignment is essentially to help you prepare for your first test on Monday. So that means that you don't have much time to do it. So I'll give only a few questions enough for you to practice certain ideas to prepare yourself for the first test. Okay, so can we have the first assignment say on handed to me by Saturday night before 12 a.m. Is that okay? Then I'll be able to share with you the solutions after that, and then you can prepare for your first test. Is that okay? Okay. I'm sorry, it's just I just had too many things before this. So okay, so let's move to the first lecture. Okay, maybe you need to know a little bit about the first test. Usually what I do is to have no, the ability for you to pick your own questions. So there will be about 4 questions altogether, and you need to answer only about 3. Okay, so those 3 questions probably have the a few smaller parts, of course. Okay, and the full mark about 10 per question, so that means you have a full mark of 30, okay, for the 3 chosen questions out of 4. Okay, so hopefully I'll get to all the things done. Okay, so let me go back to this whiteboard, and again today we're going to do some examples. Hopefully my whiteboard works. Okay, so today we'll talk about simple models of spin on lattice. Have you done solid state physics? Anyone? So I'm pretty sure you have come across a model of atoms on a lattice, right? So we are going to use some of these ideas to actually demonstrate a statistical system. So recall what we have before. Okay, let me just do some recall of what we have done. So we talked about microstates being given by quantum states. So, and quantum states include states of spin, okay, which I demonstrate at the end of the last lecture. And then we have also the idea of macrostates. Okay, and these are essentially constraints being given by constraints fixing some thermodynamic variables. Okay. Okay, so that is more or less a gist of what we have done in the previous lecture. So today what we're going to do is to be able to write down a system with some constraint, the macrostates, and the microstates are given by your quantum states. In this case will be spin states. I hope everyone is able to get in. Let me just check. Okay. So, right. I think that should be all right. So, so consider, let me just write those texts down. Consider n particles on placed on a lattice. Lattice sites. And each particle carries a spin half. So remember the spin half have two different states. So they can have spin up, which is normally denoted by an arrow with pointing in the up direction, and spin down. So you have done quantum mechanics, so I hope you understand what this actually means. This is just a cat vector which represent a quantum state. Okay. And then the spin down is shown by an arrow pointing in the down direction. Okay. And usually what happens is that we put this system placed under magnetic field, pointing in the z direction. And essentially each spin carries a magnetic moment, so they have magnetic moment mu okay, and so this mu you can give it in a sense like a vector depending on the direction of the spin in some sense, and the interaction between the magnetic moments. So essentially there will be a Hamiltonian usually interacting between the magnetic moments and the magnetic field, okay, which is usually given with a minus sign mu dot b. Okay, so in other words, for spin up, your energy given from this Hamiltonian, your energy is given by so maybe I should write this thing down first. Probably I will just write Sz spin up is h bar on 2 spin up. Okay, so that is saying that okay, this has component of spin in the up direction with this magnitude, and then you have spin down with the negative with this negative scalar in front. Okay, it's not the magnitude. Let me see, I can push this thing down. Oops. Down, up. Hopefully I can push this thing up. Doesn't seem to work. Give me a minute. I'm just trying to find where it should be possible now. Hopefully I can drag this. I don't know if I can do this. Oops. That's not what I want. Who is this problem? I just need to move this whiteboard out. Oops. Up. Okay, that's better. So okay, so now for the spin up state, you will have the energy essentially equals to, since it's there's a negative there, so you have essentially your energy will be minus okay, probably no, there will be some scalars being left out, but never mind. So essentially, your energy coming from this Hamiltonian is roughly no modulo some scalars, which are no, I'll do this properly in the notes, I suppose. It's minus mu b because of that magnetic moment dotted with the magnetic field, which is going up in the z direction. So with this negative, so you get negative ub. For the spin down state will be a plus ub. Okay. So okay, so that is essentially the state of a single particle on one particular lattice side. Okay, so these are corresponding to a single particle. Now, usually what happens in this particular case is that one needs, I can actually do this. I need to move this thing a little bit up so that I can write it better. Okay, where was I? So usually what one needs is essentially to talk about many particle systems. So in this particular case, let's suppose you have n particle states. Okay. So remember, on the lattice you might have many particles situated on the lattice side. So then one can talk about a quantum state, a collective quantum state. quantitative for the whole lattice side, given by some quantum state denoted by psi over here. I will explain I here in a minute. So I can look at all the lattice side and then start to see whether it spin up or spin down and so on and so forth. Okay, for each lattice side. So, and there will be different configurations that's available here. So your I is actually describing each each spin configurations. Okay. So let's make this a bit more quantitative. So let me just pull this up again. So, oops, that's not what I want. How do you do this? No. Okay, never mind. Okay, so what one needs is a little bit more more quantitative, so you need to fix a few things. So in other words, so here we fixed number of lattice side and lattice sides. So in a way, this is like your macro state. Okay, and that will be so that means this defines macro state. Okay, because you fix the number of lattice side, but there will be different possible configurations to each. So in other words, given a particular configuration, you might have a particular energy, okay, and then all these configurations will give you, maybe giving you the same energy, for example. Okay, so let me just write this thing down. Let N1 particles have spin up. That means there will be energy of, remember previously we had the minus sign for spin up, so minus epsilon, and N2 particles have spin down and energy plus epsilon. But you have to remember there's a constraint here. N2 will be, so remember N2 equals to N minus N1. Okay. So now one can start to think of, okay, what's the total energy of this system, or this N lattice side system? So the total energy will have to be energy, can't even spell, U equals to minus N1 epsilon from the spin up, and then plus N minus N1, which is N2, times epsilon. Okay, so in other words, if I combine these two expressions, this will give me N epsilon minus 2N1 epsilon. So in other words, here you see that your total energy or your internal energy over here depends on this variable of N1, okay, which is number of particles in the spin up direction. Okay. So again. I have to do this every time. No, it's not that one that, but I want to push it up. Okay. So now one starts to think out, okay, what would be the number of different possible states for the n lattice side? Okay. So then you have to see of, remember that this is like a function of un1. Okay. So you're picking out, you have n, capital N lattice side, and then you're trying to put n1 spin up on the lattice side. So this is again, like we have done before, this is a matter of combinatorics, the number of ways to count how you select a particular lattice side to give a spin up direction. So number of ways of choosing n1 spin up out of n. What's happening there? Never mind. Out of n, and that will be given by this symbol w, which we're going to write this as your the number of different configuration things that will define your entropy later on. Okay, will be n, capital N factorial divided by n1 factorial, n1 factorial, and then n minus n1 factorial, which is really n2. Okay, and this will also essentially tells us about the degeneracy of n particle system with energy U as given in here. Okay. And I need to push this thing out. Okay. So then we can start to calculate the entropy of the spin system on the lattice side. Entropy of spin system is now given by formula for entropy previously, which is your Boltzmann constant times log W. So in other words, W is given by this. Yeah. Oh. Okay. How long have you lost the whiteboard? Can you tell me how long? Very. Okay. You have seen this one? Okay, good. So we are just okay. In other words, what we want to do is essentially to give a particular macro state, which is now fixed by this u, and then also the number of your lattice side, and then you see the number of different configuration with that lattice side and with that energy. Okay, so and the formula is just given by kb log w, and you can just simply plug it in. Okay, please let me know if somehow you have lost the whiteboard again. factorial n minus n1 factorial. Okay. So one can you can see, you can put some numerical numbers, but I don't want to do this here. This don't want to fill up. Oops. Yeah, not so friendly. Okay, so usually what happens is that these numbers are large. Usually n and n1 are large. Okay. So there must be a kind, once you have a large numbers inside here, inside your factorial, in fact, one needs some kind of approximation so that one can actually do calculations with it. So one of the famous approximation is essentially Stirling approximation. You can look it up. Okay, we're just going to use the formula. Usually it's given by this n factorial given by square root 2 pi n what is this? Okay, now I different formula. Let me just use the different formula, the one that involves the log. So Stirling approximation involves the log n factorial here equals to n log n minus n plus some error terms. The error terms is about log n there. These are errors. Okay, so we're just going to since we have the n factorial inside here, and then you take in the log, so we're going to use just that. Okay, so for example, this is not really necessary, but you can see what's happening in the log m factorial, for example, and this is what log of m times m minus 1 until 2 times 1, for example. Then you know that you can always add this up. Oh boy, what do I do now? Where is the let's see if I can enlarge this somehow. Sorry, I'm not so used to this whiteboard thing. I only use it occasionally. I'm trying to figure out how to enlarge this. There must be a menu somewhere. No. Anyone has used this before? Can help me? Okay. It's not one. Okay. Never mind. There's some tricks that I have not learned how to do this yet. Oh dear. Probably I need another pointer device. Just give me a minute. Hope it doesn't conflict with the other pointing device. Okay, so let's see if this works. Okay, so what do I want to do? Okay, this is better. Right. So now I want to bring this up. I'll use both pointing device now. So let's see if I can make this bigger again. Okay, we're back in business. So here you can see that you can use the log properties. This will be log m plus log m minus 1, and then go on to log 2 plus log 1, and essentially one can actually write this as a sum of n equals to 1 to m of log n. So one of the things that people do is to approximate this sum using an integral. So this will be replaced by an integral of this sort. Again, there are a lot of things which have was not really derived in the main text, but you can look at the appendix. So we are just going to use it. In fact, we are not going to use this formula, in fact, but essentially you can see that it gives you all this Stirling approximation again. It's n log n minus n evaluated at m plus a half from a half. Okay, but this does not matter too much, but no, the thing is to be able to use that Stirling approximation when you want to do the calculations. Okay, so let me pull this thing up. Okay, so where was I? So now we apply this. Oops, it's getting trickier now. Apply to log w. So this gives you what? Log w previously was this. I just rewrite this thing over here. Log n factorial minus log n1 factorial minus log of n minus n1 factorial. You remember that w is what? W was n factorial divided by n1 factorial n minus n1. Okay, so when you take the log, this becomes additive in this way. So now each of these numbers are going to be large, so we're going to replace this. I should put approximate sign there. So this is n log n minus n1 log n1 minus n minus n1 log n minus n1. Now we're leaving out the term which is, let me go up, down, sorry. We are missing out this term because are you seeing the cursor? Please let me know. Can you see? Okay, great. So we are leaving out this part of the term because usually this is going to be larger because you have this n multiplied with the log n again. Okay, so in other words, this will be much larger than this number alone. Okay. Oh no, not that. I want to do is this. Okay. So so we have that as an approximation for log w, but we're going to do a little bit more manipulation, which is not shown in the book, but no, it says something. I will start with that. If I can find where my working is. Okay. So what one does in this particular case is to add and subtract a few terms. So here what I'm going to do is to write this with, let me see, n log n minus, so I'm going to, I'm going to write everything down first. Log n1 minus n minus n1, where was it? N minus n1 log n minus n1. Sorry, my eyes are everywhere, so I cannot focus. And what we do is just simply add a term and then subtract it away. Okay, what we're going to add is small n1 log n minus n1 log n. So we are not doing anything here. No, we're adding some term and then subtracting away. But what one can do with this is the fact that I can now collect terms. For example, this term, okay, and this term. If I collect that, that gives me okay, I'm trying to see where my notes are. I want to call it not that, sorry. So that's why I was confused. I want to collect this with that and this. Maybe I put double line there with that. Okay, so essentially that gives me n minus n1 log n, and then the one with the single line there will give you minus n1 log n1 over n. And we still have this term, okay, which is minus n minus n1 log n minus n1. Okay, so let me push this thing up. So that gives me, what else can we do? So you can see there's a common factor here. Okay, so I can collect that, n minus n1, and then this will be log of n divided by n minus n. Okay. The next thing to do was to, I'm going to take a factor of capital N out. So I will bring out capital N out from all the expression, and this becomes 1 over n 1 over n log of n. I could write it this way. Excuse me. If I divide this by n, then I will get the following. 1, sorry about this, the throat is dry, 1 minus n1 over n. Okay. And this one will be minus n1 over n log n1 over n. Okay. So again, you should be doing the derivation, but no, I was just helping you out here. So okay, what happens over here, you can see this is 1 over that, so I can write this 1 minus n1 over n to the power of minus 1, but then that will give you a minus sign, so that will give us the following. What's the expression again? I've forgotten now. Yeah, it's minus n n1 over n log n1 over n times, well, sorry, times plus 1 minus n1 over n log 1 minus n1 over n. And that is essentially what the book used. Okay. So we had that to be equals to your log W. Okay. So log W is all the way up there, so I'm just writing it there. Oops. Oh, no. Okay, and then more or less we have almost completed the calculations now for your entropy, given that you have calculated your log W. But let's observe another thing. Recall U, which is, let me just check, our U was equals n, where was it, n epsilon minus 2n1 epsilon. Okay, and then if you take the energy per particle, will be U over n, the total energy divided by the number of particles, okay, which is equivalent to the number of sites. This will give you epsilon minus 2 epsilon n1 divided by n. Okay, but now one observes this. Your energy per particle is an intrinsic quantity. Okay, because you divided by the number of particles there. So in other words, that energy is really independent of your number of sites. So if you look at the expression on the, so this is independent of capital N. So in other words, the right hand side also should be independent of capital N. This term is of course independent of capital N, but this term has this behavior. So in other words, what we can conclude is that n1 over n will be independent of n. Okay. So these are just physical arguments that one use so that when one observes what's happening over there, okay, is that, okay, what you see over here, that you have all this n1 over n, n1 over n, n1 over n, this is not w, this is n, okay, n1 over n, right? But n1 over n is actually independent of n. So in other words, the entropy over here, okay, which is S equals to KB log W, okay, then you find that, okay, this is only dependent on n, which is the one apparent outside. So this is proportional to it, because the terms inside the curly bracket is independent of the capital N. Okay? So in other words, this is sums up with what we already know about entropy, because entropy is supposed to be an extensive variable. So the larger the system, okay, so let me just write this thing down first. Larger system, which means in this particular case of the lattice side will be larger n, and that gives you larger entropy. Okay, so that is essentially what it means by extensive variable. So that more or less sort of finishes up your spin system, almost. There's another thing that the book does, which is looking at the equation of state for the spin system. Okay, so let's do that. Maybe this is a good point to take a break. Is that okay with everyone? Are you still with me, or I'm still with you? Okay, we'll take a say 5 minutes break. Okay. Okay. I hope everyone is back. Okay, great. So let me just continue. Okay. So the next thing what the book does is essentially to work out some idea of a state equation or equation of state related to the entropy in a way. Okay, so let me just write things down here. So so this is just continuing from the spin system. Continuing. The idea is to be able to write down some relationship between different thermodynamical variables, which tells you the equation of state. Okay. Continuing with the spin system. So one of the things that we already seen before, so I'm just going to rewrite everything. The energy per particle is given by, oops, is that right? Oh, no, man, I'll just write this thing down. I just need to check the one before. Okay, the one before was essentially this. Let me just write this thing down. So the one before we had U over N to be your, previously, U over N is energy per particle. And this is given by epsilon minus epsilon 2 n1 over n. Okay, so there is a common factor of epsilon there, so I'm bringing it on the other side, so I get u on n epsilon equals to 1 minus 2 n1 over n, and I'm going to write this to be equals to x, and essentially your x is really, let me just check. Your x is really equals to n1 over n, sorry, not that, Control Z. Okay, the relationship between n1 over n with x is the following. Okay. And then the other relationship, please do check this equation. I did check it my own. So the other set of equation will be 1 minus n1 over n, and that gives you 1 plus x over 2. Okay. So we're going to use this slightly simplified variable using your x's to write down your entropy. So your entropy is now given in terms of x as shown over here. It's 1 minus x over 2 log 1 minus x. Why is there a triangle over there? 1 minus x over 2 log 1 minus, oops, push this thing up so I can write properly, 1 minus x over 2 and then plus, I should really write that so that it doesn't get confusing there, 1 plus x over 2 log 1 plus x. Okay, so now it's well, it's the same as before, but now you replacing your variable of n1 by this variable x. So what we're going to do is to recall something that we have done much earlier about the relationship between temperature and the entropy. Okay, so recall earlier, which is 1 over T equals to partial S partial U at constant volume. And for this, we need to change the, here we are differentiating with respect to the internal energy, but we would like to make the derivation with respect to x over here because we have changed some variable with respect to x. So we do a chain rule. And then that means we need to take the derivative of x with respect to u. But then you already seen before what's the relationship between x and u is x equals to u over n epsilon. Okay, So dx du will be 1 over n epsilon. Okay? So in other words, now we can write ds dx, which we have not done yet, times 1 over n epsilon. Okay? So all we need to do now is, oops, what did I do? Going all the way up. So all we need to do is now to differentiate your entropy with respect to x. So let's just do that. And that will give you the state equation. So ds dx. So you differentiate x over here, so there's a minus x there. Your minus will cancel the minus in front. Or maybe I just put everything inside this. Then it will be easy. Then I will just have this minus x over 2. So that give me minus a half there, and log 1 minus x over 2, and then that's differentiating this factor. Then I have to differentiate that, so that gives me plus 1 minus x over 2, and then your log will turn into what you call the reciprocal. So that gives me a 2 over 1 minus x. But then you have to remember again what's happening. Then I have 1 minus x over here, but then I have to remember that you have this minus sign, so I have to multiply with minus sign there. I think that's it. Hang on, let me check. Yeah, and then you do the other term, which is now plus a half log 1 plus x over 2. Okay, that's differentiating that factor, and then you do the differentiating the other factor. That will give me plus 1 plus x over 2 times 2 over 1 plus x, and since this is plus 1, so I don't have to multiply with anything. Okay. So that gives me the derivative there. So let us simplify this. So here you have 1. I hope you can see the cursor. Here you have 1 times minus 1, and here you have 1 times 1. So in other words, this will cancel off, and you're left with minus n kb over 2, factor of 2 coming out, half, sorry. And then you have a log of 1 minus x over 2 with a minus sign, and log, where is it, the other one? Again, I'm not sure why. Okay, this is log 1 plus x over 2. So you combine these two together, then I have a log of 1 plus x divided by 1 minus x. Okay. So plug this thing into the previous equation, which is this one, 1 over t equals to that. So let me just rewrite everything here. So this gives me 1 over t equals to minus nkbo2 log of 1 plus x over 1 minus x, and then remember we have the other factor which is 1 over n epsilon, right? So your capital N cancel off, this cancels off, and rearrange this equation. That gives me 2 epsilon over kbt equals to log of 1 plus x divided by 1 minus x. So you take the exponential of this, and I'll have exponential 2 epsilon on kbt equals to 1 plus x 1 minus x. And there are a few more steps which I'll let you try to explore yourself. Then you should be able to write your x. Okay. Your x is, if I got all the steps in, so I don't want to make it too easy for you. Your x is equals to E minus epsilon on kbt minus E epsilon on kbt divided by E minus epsilon on kbt plus E epsilon on kbt, which is a familiar kind of expression that you should have seen before. The top one is related to your minus hyperbolic sign, and the bottom one is this one is minus hyperbolic sign, this one is hyperbolic cosine, okay, or cosine sign. Okay, so this will give you minus tangent, hyperbolic tangent epsilon on kbt, and remember that this x is really what? U on n epsilon. Okay, but let's see what is u. U is really what? U is really your minus n1 epsilon, the number of spin up, plus n2 epsilon. So I can rewrite this as follows. N1 minus N2 equals to minus U on epsilon. Okay. And what happens there, if you combine these two equations together, I have N1 minus N2, N2 equals to capital N hyperbolic tangent epsilon on kbt. Okay, so by using the fact that we have used the thermodynamic relation of entropy with the temperature, we are able to derive this. And this is what, remember, this is number of spin up minus number of spin down. So one could actually relate this with another thing which is called the magnetic moment. Okay? Because the number of spin up minus number of net spin, if you like. So this will give us this idea of magnetic moment per unit volume. So So you divide it by the volume of the following nature. M equals to mu times n1 minus n2 divided by v, and this is equals to mu n over v times hyperbolic tangent, and then epsilon is equals to mu b. Okay, then we have mu b over kbt. So all that long-winded working is just to give this idea of, okay, you are able to relate the state of the system through which is your number of spins up and spin down with temperature, and then this will also give rise to you to the idea of a magnetic moment of the whole system. So okay, there are a few more examples in the book, which is one of it is probably vacancies in a crystal, and then the other one is model for the rubber band. I'm not sure which is much more important, but in terms of accuracy, the one for the vacancies in the crystal is better, because the rubber band is a sort of, there is a sort of a gross simplification. So probably I will just do just the vacancies in the crystal. Okay, I think I better start fresh. So let me clear the canvas. Okay. So now we look at the idea of vacancies in crystals. For the notes, I will include the rubber band as well. Okay, so just for completion. So one of the things that people do when you look at crystal is an orderly, basically, how should I say, a system with orderly arrangements of atoms. But most of the time, what happens is there will be defects. Okay, so the defects are sometimes caused by vacancies. So instead of having an atom on that particular site rising from vacancies, so essentially these are missing atoms from lattice site. And usually what happens in this particular case, there's some energy involved. So essentially when you sort of remove an atom from that lattice site, there will be energy involved. So the defect maybe I should write differently. Each defect, I mean each missing atom, will have some energy. Okay. So if there are n defects, then that will give you total energy of defects and epsilon. Okay. So what one can try to do is to see the kind of macroscopic state of this defect. So suppose defects occur at certain sites, say occur at sites, say alpha, beta, gamma, and so on. Then one can assign some microscopic state, so a quantum state, which is given in terms of that location of the site. Okay. So again, this is just an abstract idea of a defect kind of wave function in a way. Okay. So and different defect configurations give independent quantum states. So so now we can start to give some kind of a quantitative kind of flavor to this by saying that, okay, suppose you have n atoms in the crystal, and then there are n, small n defects in crystal. So that means really what you have n, capital N plus small n lattice heights. Okay, so now the number of different arrangement of the vacancies, different vacancy configurations, you can count them. Okay, they are essentially given by n plus n, which is the total number of sites, divided by n factorial, the small n, which is corresponding to the defects, and then the capital N corresponding to the number of atoms. Okay. So now you can write down. So this is essentially your W. Okay. So one can start writing down the entropy for that. So S equals to KB n plus n log of n plus n minus n log n minus capital N log capital N. Okay. And we're going to relate this with your internal energy of defects. Which is n epsilon. So again, to make this thing sort of related to the temperature, which is the thing that we need in statistical mechanics, is to write down the relationship between temperature, sorry, this should be 1 over T, between inverse temperature, really, inverse temperature with the derivative of your entropy. So this is a derivative of entropy with respect to U, but I can now rewrite this as the derivative with respect to number of defects. Okay. and you can calculate that. So this is KB on epsilon log of n plus n. So in other words, you take the derivative with respect to n over here, and then derivative of that log, which is now giving you n plus n over n, and then take the derivative of that. So I have n there, so I have minus log n, and then minus n over n. Simplifying this, then you get KB on epsilon log of n plus n over n, and then you do the same trick like before. You try to rearrange this equation. I will get, for example, exponent of epsilon on kbt, okay, equals to n plus n over n, or 1 plus capital N over n, and rearranging this gives me small n over capital N equals to 1 over E epsilon on kbt minus 1. Now usually what happens that this number of defects are much smaller than than the number of atoms there. So these are much less than 1, which makes sense because we have that thing there. Okay, so one can actually give some estimates of what you see in practical situation. The typical value of epsilon for your defect is about 1 eV, and you can actually try to do calculations over here at room temperature, for example. Your epsilon on kbt is given by this number 39. Please check that for me. I did not check that properly just now. And plugging into this expression, that will give you essentially your defect density in some sense. Okay, not really the volume density, but the ratio with respect to the number of atoms there, which is really about 10 to the minus 17. Okay, so essentially that tells us, okay, it's just a small number of defects coming in. So I think I do not want to go into the model for rubber band because it doesn't give you the really right answer, but it just gives you the technique of how to model things. I'm not quite sure whether I should do that or not, because there are some tricks inside there. One of the tricks, maybe I should just do this straight away. So let me just move this thing up. So you have a model for rubber band. I'll do the one that was not really written down properly in the case of the book. So you model it by a long chain, modeled by a long chain of atoms. So in the so-called maybe I just write it down. Okay, rubber band being pulled, so everything gets pulled the long chain of atoms being pulled there as well. So that gives a chain of atoms which are linear. But other configurations, you have, instead of having a linear chain, you will have links. And the way how your chain of atoms having links, there will be many numerous arrangements. And hence, because of that, you have a huge entropy. Okay. So one could do this in a simplified way. Your links will have two directions. Have two directions over here. Took me quite a while to think about what does this mean, but no. So that's why I think I better just do this so that you understand what's going on in the book. So, and this is counted, the number of links which has this positive z direction will have n plus over there, and the one with the negative z direction will have n minus. So you start thinking in terms of the different directions of the links, and then you consider configuration of these links to give you a particular microstate. For example, psi I is given by, say, you have a plus link, and then minus link, plus link, plus link, plus link. I'm going to write this all out, which is the same in the book. How many plus are there? 4 plus, minus, another 3 plus, and then minus, plus, minus, plus, plus. Okay, so this is sort of a state, a microstate that describes the possible types of links for the rubber band. Okay, so you can, if I did it correctly, there should be 11 positive links, and then 4 negative links in this particular example. And this was actually shown in the book. So let me see if I can insert an image here. Image. Okay, where's that? Yeah. Okay, let me enlarge that a little bit. Okay. So here is essentially correspond to the state given shown here. So your plus in the beginning over here, this plus, okay, I hope you can see my cursor there. So this plus correspond to this plus. This go in the opposite direction. Is that minus? And then you have a plus, a plus, a plus, and a plus, right? Are you seeing this? Please confirm.
Yes.
You can see the cursor, right? Okay, and this is a minus, and then you have a plus, okay, minus there, then you have 3 plus, 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 and then a minus, and then a plus, and then a minus, and then a plus, plus at the end. So this sort of gives you the kind of possible configuration of the links inside your rubber band, so to speak. So you can have different configurations, of course. So I'm not going to go all through this. And what it does is to look at all the different configurations and then try to calculate things with it. Okay, so here one of the things that it says, each link has length d, and the rubber band chain as a whole has length L. Okay, so again, I'm highlighting things which are not so clear in the book over here. Okay, so what I'm trying to say, it says that the figure that you have here has length 7D. Okay, how do you see that? Well, it's just you take the number of positive links minus the number of negative links, so that is essentially 11 minus 4 times the number of links, which is D. Okay, so that starts to you start to quantify things, and then because of the possible changes of length that one can have, then one can talk about your tension, for example, okay, times the changes in length, okay, and then you start to write down your thermodynamic equation over here, du equals to T ds. Oops. To do things too fast. T ds plus F dl, and your ds again will come from this kind of configuration, but now you have to have a macroscopic constraint, which is given by this 7D. Okay, so you fix this 7D configuration, so you can have all the plus and minus, but now of a different order, and then you start to count the number of what you call different configuration that you can actually have, which is n factorial divided by n plus factorial n minus n plus factorial, and so on and so forth. So again, all these things are similar to the ones to the examples before, but of course this is a very crude model of a rubber band. So the conclusion you can see, you can read in the book itself, it gives you the wrong answer. Okay, so I will stop there for today. Okay, let me go back to you, and let me get your attendance. And let me download that. Okay, I will let you know when the assignment is up. Okay, I already choose a few questions, but not all yet. So that's why I need some time to do it, so that I can see what is the best thing for you to know, and let that be given to you to see whether you understand or not. And then perhaps in the test, as I said, there will be 4 questions. You choose out of the 3 questions, and they will not be the same as the assignment questions, but what happens over there, I will make sure the questions, the test questions, the techniques to solve them is already known to you through the assignment. Okay, so any questions about the test and assignment, let me know before we stop this. So I hope you have a bit of time, well, not much time. I'm sorry about that. You have a bit of time to look into the assignment questions until say late Saturday night or early Sunday morning. Okay, and then I'll give you the solutions. Okay, and then on Monday at 10 we have our first test, and then that will finish off until 11:30. Okay, that's all for today, and then I will end this meeting now. Thank you, everyone.
Thank you, Doctor. Thank you, Doctor.
Okay, bye.
Thank you, Doctor.
Bye, Doctor.